Thanks. Okay, so thanks for the organizers for doing this, like Misha and James and other people. It's actually a lot of fun. So I'm Sham Kakade. I'm at Microsoft Research New England. The question I'll be looking at today is how do we learn latent variable models or models with hidden factors? And these are models which are pretty useful in a variety of settings because we like to find reasonable representations of the world. And often, if we can get better representations of the world, they will help us in technological applications. So, a couple of days ago, Vikas gave this very nice talk on speech, deep learning, alternatives to deep learning methods in the audio domain. And inside this pipeline, a lot of the major advances really came from different acoustic representations. And we're trying to tease these things apart. But there is this sort of widespread belief, if we can really get better representations of the world, we'll get performance bumps on tasks we're interested in. And in this talk, we're going to look at two natural models for the ways in which we represent the world. One is this mixture of Gaussians problem, where we see points in space, looks something like this, and I say, tell me the means. Okay, so there's some underlying data generation model, and we want to figure out the means. And a harder question for this model is, suppose your data look like this. Now, this is a neat question because in this case, you kind of clearly see these guys have different means. This case is pretty neat because they're right on top of each other. You can think of this as the mean zero mixture of Gaussian case. Okay? And this is a much more challenging question to learn because, in a sense, you're mixing up PSD matrices. But we'll look at this question as well. Okay? So there's an abstraction, which is how do we learn Gaussian mixtures? And there's another problem of how do we learn topics and documents. So these are models where we have a set of documents, and we think each document has one or more topics inside it. Okay? And we see either collections of documents or collection of points. And how do we learn these? Okay? And in particular, we'd like estimators where we get some statistical guarantees along with computational guarantees. Okay, so here, the basic question is, what are the limits of what we can learn, both computational and statistical? And for these Gaussian mixtures, there's a very nice paper by Ankur and Greg really showing that for reasonably well-separated Gaussians in 1D, you're going to need exponential number of samples in K, where K is the number of Gaussians. And it's an information theoretic lower bound. Okay, so at some level, we can't really expect to learn these things all the time, even when they're reasonably well separated. I mean, they still are close together, but it was an information theoretic lower bound in 1D. There's been various results about hardness for maximum likelihood estimation in these models, which is slightly different because that's not an information theoretic hardness result. So the question is going to be under what assumptions and models can we learn, and how general can we make these things? Okay. So this work is going to review a line of work that we've been involved in, which basically is arguing that under many natural settings, some of these hardness results don't apply, and we actually learn these models, like the spherical mixture of Gaussians case and subtopic modeling cases. We basically do this with simple linear algebra approaches, basically generalizations of SVD. And these aren't convex optimization problems, yet we can still do them. Okay, but there's a pretty, at least recently, a bunch of my research has been switching gears, but one question that's been on the back of my mind is this learning mixture of general Gaussians, because there's sort of one trick we used in the line of work here, and we're really wondering if this was limiting, and are there really barriers when we start looking at more general cases? And I think this is really the hard case for the mixture of Gaussians. Take a mixture of zero mean Gaussians, they're right on top of each other, and you're effectively getting kind of a mixture of PSD matrices. And recently, we've shown we can actually solve this, and I'll highlight some of the results there as well. But it's an interesting tensor because the tensor is arising not in a pure sense. It's arising from a mixture of PSD matrices. So I'll briefly discuss that and highlight this new result. But it's kind of a different set of ideas. Okay. So, yeah, so in terms of related work, there's really quite a lot of related work. I can't go through all the details, but in the theoretical computer science community, there's been a lot of very nice work when we have separation assumptions, how we can learn these things, and then when we don't have separation assumptions, there's some nice work starting with Adam Kalai and co-authors and Misha Velkin and co-authors of how we can learn mixtures of Gaussians in an information theoretic sense. In topic models, there's also been a nice line of work. In a sense, I would say this line of work really traces back more on the statistic side from the statistician Joseph Chang, who originally understood identifiability of phylogeny trees, and that led to some nice work by Al Hanan and Sebastian Roch on learning phylogeny trees, which eventually influenced our ideas. And then we realized the connections between many different communities. Okay, so let's, and definitely ask questions. So let's just go through the model slowly and tackle the problem. Okay, so let's set things up. So mixture of Gaussians problem. Right? Think of having k means mu1 to mu k. Okay. And how are we going to generate our data? First, we're going to sample a cluster I with probability wi. Then, for now, let's assume we have spherical noise. We're going to get a data point x, which is a mean, plus some noise where the noise is perturbed by some spherical Gaussian noise. And our data set is going to be just a bunch of points in some space. Okay, so we're clear with that? And the topic modeling case is the single topic modeling case. And we're going to work in the statistical setting. So we've got k topics. Think of mu1 to mu k as multinomial distributions. Okay. And we're going to sample topic I with probability wi. And then the way we get a document is we take our multinomial distribution and get m draws of words from this particular multinomial distribution. Okay, so then our document, which is going to be x1 to xm, is going to be m draws. So these are each some atoms in a set, sampled independently from ui. And then we get multiple documents, which are collections of words. And we are ignoring the order. So is the setting clear? Okay, so, and the game is, how do you estimate things? You're going to either see points, or you're either going to see documents. And your goal is to tell me the mu's, w's, and the spherical covariances. And for this zero mean case, just to set it up, just think about this in parallel. There the parameters are wi and a set of PSD matrices, sigma I. And we're going to sample I with probability wi. And we're going to see x from a normal, which is mean 0, and covariance sigma I. So this is a sort of significantly more challenging problem. Okay. So are we good with notation here? And what's the game? Well, we're just going to look at the method of moments. We'll start laying out these moments and try to see if we can invert them. This is an old idea from Pearson. Look at the structure in our problem. Try to find the parameters consistent with this problem. And this is going to make some nice connections to tensors and linear algebra, because this is really this classic inverse moments problem. But what's interesting is for this mixture of zero means Gaussians, it'll actually give rise to a rather different moment structure than we've seen before, because it's coming from PSD matrices. Okay. And this question is kind of interesting for the topic model case, because, you know, let's look at the moments for the mixture of Gaussians. These are just the mean, like a covariance matrix, and then three-way correlations. But for the topic model case, the moments are interesting, because what's the first moment? It's just the average distribution over the words in the language. What's the second moment? You can think about this as being specified as the distribution over pairs of words in a document. Right? So it's a bigram distribution. What's the third moment? It's just the distribution under which three words tend to appear together. Right? And this inverse moments problem is interesting because suppose every document had one word in it and you had an infinite collection. All you could get is the average distribution of words, and it's clearly not identifiable. It's not even a statistical sample size issue here. It's just not identifiable if every document has one word in it. So if we have, if we're going to solve this problem, at the very least, we're going to have to be able to understand how many words in a document do we need to have before it's identifiable. So are 2 words in a document enough to get identifiability, and so on. Okay? And that's why these identifiability proofs, while sometimes they're tricky, if we can make them, if we can think about this issue and maybe make it algorithmic, it gives us some way to address these problems. Okay. So this is the game. We're just going to start looking at some moments and try to invert them.
Sham?
Yep.
When you have probability x1, x2, I assume this is a co-occurrence probability.
It's a co-occurrence probability of 2 words in a document.
Right. So if I have a particular document where x1 actually appeared twice and x2 once, that's still counted as one co-occurrence?
No, think of it as just a. Okay, so think of this as just a bag of words model. So then you would be just estimating. If they were ordered, then this isn't an issue at all. So for simplicity, think of the first word, second word, third word, and you can estimate that, and then just make it make it symmetric. So yeah.
I guess the question is, it's not just co-occurrence, right? It's frequencies. Aren't you counting frequencies? Multiple occurrences mean something different from one occurrence, right?
So one way to estimate this quantity. So let's just say every document had 2 words in it. Just for simplicity. The way you'd get an empirical average of this is just the expected value of the indicator function of those 2 words appearing.
What if it has more words? Are you going to count the numbers? I mean, this is
so think of just just think of getting any reasonable unbiased estimate of this quantity, and then you would count the numbers appropriately. So think of just one way to do this is just sample from the document, compute the empirical expectations. But there's an easier way. You definitely are going to utilize more words per document. But for now, just think of this as you're getting better unbiased estimates of this quantity.
So you'll take the frequencies and adjust them appropriately to get.
Yeah. So think of it just like.
So all I'm asking is, frequencies matter or just occurrence or not?
Frequencies matter.
That's the question.
That's right. And in fact, for now, think of these as separate questions for now. Suppose I just give you exact moments, because once we think of approximate moments, it was actually just how this sampling issue, just how do we estimate these? And then if we have more words per document, we're going to get better estimates of these, where the frequencies matter. But for now, let's just suppose we have exact moments. But certainly in practice, we would absolutely use the fact that we have more words in a document. So just use vector notation. It's nice. So mixture of Gaussians, x is going to be a vector in d dimensions. Suppose we have k Gaussians. So a nice thing with conditional expectation is the expected value of x, given it's from cluster I, is just the mean. Good with that. And the nice thing about the topic modeling case, we're just going to treat words as vectors with this hot encoding. So the first word we'll treat as a vector of 0 with 1 on and then 0. So this means the second word in our vocabulary occurred. Right? And this is convenient because we can say the probability of a word given topic I is just the expected value of x1 given the topic I, which is mu I. And we just think of these topics as probability vectors in space. Okay, so we get just with this notation. So this is convenient because we can write out moments and use linear algebra. Okay. So now let's just start looking at some moments and see if we can invert these things. So the first moment's simple. Right, so what's the first moment for the mixture of Gaussians problem? It's just the average of the mu i's. Okay. What's the first moment for the topic modeling problem? It's actually just also the average of the mu i's. This notation. You good with that? Okay. Let's just compare this to this problem for a moment now. So first, are we good with these moments? Right, these are pretty straightforward. Okay, so let's look at this problem for the mixture of zero mean Gaussians. Here the first moment is 0, because everything's zero mean. So it's sort of natural to compare it to the second moment here. So what's the expected value of XX transpose here? It's actually just the average of the PSD matrices we see. The mean is 0, but the second moment for this mixture of covariance matrices is just the average covariance matrix. Okay? Because in a sense, this mixture of zero means Gaussians is like getting, it's sort of like XX transpose is the natural quantity to look at, because in expectation, those are the sigma i's conditioned on which Gaussian it's from. I mean, this is a true statement. And either way we cut it, if I give you these quantities exactly, you can invert them. Right, if I tell you, here's a mean for the topic modeling case, or here's the covariance matrix, and I say, tell me the parameters of the model, you can invert it. Yep.
So how are you doing the weights for the topic modeling? Is there like frequencies being used at all?
So yeah, so WIs are the, let's just say each document has one topic. Let's do the simplest case, and WI specifies the probability of a document having topic I. Right. So the way you draw the way you generate a document is first pick a topic, pick topic I with probability WI, and generate the words according to the corresponding multinomial distribution. Good. So now things start getting a little more interesting. So let's look at the second moment. So the second moment, for the mixture of Gaussians case, where in the spherical case, let's just assume for the spherical case, all of the variances are the same. So then you're going to get, when we look at the second moment, we get mean plus noise. So we get one term, which is like how the means relate to each other, plus this additive term, which is due to the noise, sigma squared times the identity. Right? And for the topic model case, we look at the joint distribution of two words. Because the words are generated independently, it just looks like the sum of WI, mu I transpose. Okay. And we good with this? And now the game is like, suppose I just gave you this exactly, and I said, can you tell me the mu's and sigma for this case, or can you and the w's, and can you tell me the w's and mu's here? You should think of this as a math problem now. I give you these moments, can you invert them? Turns out it's still not identifiable, and it's not identifiable in even the topic modeling case. If you impose the probabilistic constraints, it's really not identifiable, and it's sort of not identifiable on every problem. So I think even Joseph Chang in his paper for phylogeny trees gave an example that it really is degenerate. So 2 words per document aren't enough. So it's still not identifiable, but parameter cutting suggests we're getting closer. Actually, let's look at this question for the case of mixtures of zero mean Gaussians, because now let's look at the fourth moment. So what is the fourth moment of a Gaussian with zero mean? All right, so we're going to look at the expected value of the fourth moment, and let's look at the coordinates I, j, k, l. Okay, and let's do this for a single Gaussian. So this is a Gaussian with mean 0, variance sigma. Well, there's these counting theorems that tell you how to specify this, but you know what? I'll just write it out. Basically, I'm just permuting these indices, so you get the matchings correct. Because in 1D, what is the fourth moment of a Gaussian? It's 3 times the variance squared. Okay, and the generalization for this for the multivariate case is this object. And basically, you're looking at all perfect matchings of your 4 indices. So this is just the structure of these moments, but this is just for one Gaussian. Okay, and you just call this condition on sigma. And what you're going to get for the fourth moment in the zero mean case is a mixture of these objects. So call this M4 of a particular Gaussian. That's expected value of 4th power of x, condition on sigma I. And what you're going to observe is the average fourth moment over the Gaussians, and suppose I give you this object exactly. So this is a tensor that's been constructed of PSD matrices, and I'm going to ask you to tell me these PSD matrices. Turns out it's not identifiable here, but it's a much more delicate question of how you recover this object. So we'll keep going. But we see, there's interesting structure in these problems. This one is the simplest. So what's the rank of this object? K. Right? Whereas this thing is full rank. Okay. And then, of course, for the mixture of zero-mean Gaussians, when we look at the fourth moment, this is a confusing object. But it's neat. And these sort of these counting theorems kind of come up often in CS theory. Yep.
This is a bit tricky, right? Because you have the dimension and the number of components interplay, right? In low dimension, for example, you clearly don't have enough parameters.
I haven't discussed identifiability at all. This is just, this is a tensor of size d to the 4. And I'm just giving it to you exactly.
But when you say that it's not whether it's you can recover or not can recover,
you can't recover it at all, even in high dimensions with the fourth moment.
So
even the fourth moment, with the fourth moment, we have examples with two Gaussians that this isn't enough to recover the sigmas. Yep.
For mixture of Gaussian single topics, is the root of the issue here that rotations of rank 1 decompositions are still rank 1 decompositions?
You can think of it that way, yeah.
There's nothing more going on than that?
Yeah, I mean, the topic modeling case is a little more subtle because you have this constraint that these have to be in the positive orthant and sum to 1, which is why maybe this has teeth, but it doesn't, is the bottom line. But parameter counting suggests you're getting close. But in a sense, this is exactly the right intuition because the amount you're off by, sort of the thing you need to specify is basically the number of parameters for a rotation. But that is exactly the right intuition. We're trying to, right? Because suppose the noise was 0, and I just gave you this object, and I said, tell me the mu's. You can't do it. And it's exactly for the reasons you mentioned. So let's go ahead and proceed. And for now, let's just look at the single topic model, because that's the simplest case to look at. And once we figure that out, we can come back to the other ones. Okay, so yeah, so it's pretty clear just what the structure of the three-way correlations of a single topic model are going to look like. Right? It's just going to be as if the three words were generated from the same topic, summing over wi. So we're good with this. So now we've just phrased this as and let's just forget about the both mixture of Gaussian problems for a moment. But we can see, if we look at the sixth moment of a Gaussian, it's going to be more complicated ways to swap indices. And we'll come back to that moment. But we'll just look at this case because it highlights the problem here. And let's just think of this as a math problem. I'm going to give you a matrix. I tell you it has this structure. I'm going to give you a tensor. So this is a d-cubed object where each entry specifies the three-way, the probabilities of three words co-occurring. Just think of this as a math problem. I give you these objects, and I ask you, can you tell me the mui's? And if you can, then it's identifiable if they're unique up to permutations. And basically, we've seen this problem come up many times in this workshop because this is just a tensor decomposition problem. Okay. And this is nice. We've really just reduced this problem to a tensor decomposition problem. And just to show you this is easy to solve, suppose we made this second moment the identity matrix. So we did a linear transformation to make it look white. So I'm going to give you, what does that do? That basically, in this new coordinate system, that basically makes these mu's orthogonal to each other. Okay, so we can reduce the problem now to, I give you a matrix, which is the identity, and I give you a tensor where it has this decomposition, and I tell you the mu's are orthogonal. So now it's just an orthogonal tensor decomposition. Okay, and if I didn't have this mu here, what is this decomposition? It's the SVD. So this is really just the standard generalization of an SVD. And of course, the way you solve it now is Well, there are many ways to solve it, but you could just say, find me the eigenvectors of the tensor. And by eigenvectors of a tensor, I mean, when we hit a matrix with two vectors, we just mean we sum out the indices. When we hit a tensor, a 3 tensor with 3 vectors, we just sum out the indices in the usual way. We can define an eigenvector similar to how we define it for a matrix. So for a matrix, we define an eigenvector as we take our matrix, hit it with a vector, and it's stable under the vector. For a tensor, we can think about hitting the matrix with a vector twice. Let's look for stable points. And if you think about what that means here, let's hit this tensor with a matrix. Sorry, hit this tensor with a vector twice. We get this expression, right? Because when we hit it with a v twice, we're really just hitting the mu i's, and we're trying to find a solution for this equation. And since the mu's are orthogonal, what v's satisfy this? The mu i's. And that's basically the solution. And that's sort of why this, and that's really the identifiability proof as well. So what did we need for this to work out was sort of your point. We need the dimension of our vectors to be sort of the number of mu i's that needs to be smaller than the dimension we're in, because we need this whitening step to work out, which means we need these vectors to be linearly independent. Okay. And as long as we have that, the whitening will work out, and this thing has a unique solution. A unique decomposition. It's not too hard to show uniqueness. So now it's just a perturbation argument, and how sharp can we make these bounds. But this basically gives us the idea for the single topic model. And basically the algorithm now is estimate your empirical moments, find the tensors, and that's how you solve the problem. But the first theorem is just the exact case. As long as these topics are linearly independent, then we have the identifiability that these eigenvectors are the topics. And I say robust just because there's some kind of saddle point. Ignore the, there's basically a few unstable eigenvectors. Yep.
Right, so just to make sure I'm getting the parameters right, does this say that for topic modeling, that I need the length of my document to be the number of documents in my corpus to get the dimensions to match?
Yeah, so you need this says the length of your document needs to be 3, because with 3 words per document, you can estimate the trigram probabilities. See, what am I using here? I'm saying
what's the ambient dimension?
Right, so the ambient dimension, right, so the ambient dimension is we've got k topics, okay, and these topic probability vectors are in R to the d, because we've got d words. Okay, and we need k to be less than or equal to d for this to work out.
Okay, so number of documents must be less than number of unique words.
In the language, yes. But we only need 3 words per document. Okay. And that's and basically it has to be generic. So if they're linearly independent, this will break, but sort of under any reasonable smooth analysis model, this is fine. And now in terms of sample complexity, well, it's just how do we do this? Well, you just get empirical estimates, and you run this algorithm. It's a little delicate because now you're decomposing a perturbed tensor, so you need to do a perturbation analysis. And there is a little technical machinery here because unlike in SVD, there are these nice matrix perturbation theorems, which is take your matrix, compute an SVD, and we can relate the SVD of a perturbed matrix to the SVD of a true matrix. These are like Davis-Gahan theorems and Whedon's theorem. For tensors, there's no such analog because you can't just do a tensor decomposition of a perturbed tensor. You need an algorithm to do it. But basically what we can show is with a small number of restarts, just running the power method will converge to some eigenvector that's close to a true one. So basically in this paper, we get an analog of essentially these matrix perturbation theorems for tensors. And I think without further assumptions, it's the sharpest we really know how to do, at least for the under complete setting. And what's interesting is for these tensor cases, you don't really need eigengaps because every tensor is stable on their own. We don't need any, the eigenvalues could be the same and you're still going to recover them because of this third power there. And so that means basically the accuracies in our perturbation theorem depends on some kind of tensor error epsilon divided by the eigenvalue of the tensor. So there's no eigengap, which is nice because that's what allows, because it would be problematic if we couldn't figure out these eigenvectors when the eigenvalues were the same. And that's not an issue here. All we really need is the eigenvalues to be bounded away from 0, and that's what governs the statistical difficulty of this problem. So we're good with basic. And at this point, right, at least for polynomial types of guarantees, we just figure out the sample size we need to get a certain accuracy on this triplet counts. So it's just how many documents do we need. And then we plug it into this perturbation result. And this perturbation result is really has nothing to do with this particular problem. It's just for any tensor which an orthogonal decomposition exists. This gives you sort of a nice perturbation bound, along with an algorithm too. And I think it's the sharpest. Without stronger assumptions, I don't know how to make this bound sharper. Okay, so now let's go back to. So we're good with this. This is just the simplest case. But this really highlights the game here, right? At least, can we take our latent variable model and try to massage it into a problem we know how to solve? And for the most part, there are few classes of higher moment decompositions we know how to solve. Are you good with this? Okay, but what about the spherical mixture of Gaussian case and actually this harder mixture of Gaussian case? So we can back up a bit and just see how we can solve those. So what went wrong in the spherical mixture of Gaussian case? Well, we have this additive term here. Right? And that's just for the second moment. But what is this sigma squared? Can we figure it out? If I just give you this matrix, can you tell me what sigma squared is? Suppose it's k less than d. Any guesses?
It's the smallest eigenvalue.
Smallest eigenvalue. And intuitively, it's basically, as long as k is less than d, you kind of have to have variance sigma, at least variance sigma squared in all directions. So just find the direction with minimal variance, and that's basically the direction, not in the subspace spanned by the means, and that's sigma squared. But mathematically, it's just the smallest eigenvalue. Okay, so you know sigma squared, so you can subtract it off. And now the point is, for the third moment, for this problem, you're just going to get some extra terms that have to do with sigma squared and lower order moments. So you can just write out the structure of the third moments, subtract some stuff off, and reduce it to the same problem we can solve. And it's delicate if the variances weren't all the same sphere, coming from the same sigma, because then this trick doesn't work, and we can solve that. But basically, this is the right idea, that you can get sigma squared as the minimal eigenvalue, and you look at the third moment, and you can manipulate it. So here's the reduction for the mixture of spherical Gaussians, when the spherical variances are all the same. Grab sigma squared as the minimal eigenvalue, subtract it out the second moment. And for the third moment, what's happening? You're really just, what's the third moment of a single Gaussian, single scalar Gaussian? The third moment is really mu plus 3 sigma squared times mu. That's the mu cubed. So with the scalar Gaussian, this is the third moment. And basically, we just want to get rid of this stuff. And it turns out if you just, these EIs are the standard basis, but think of this as just like 3 mu sigma squared. So you subtract that out, and you make basically tensors exactly of the same form. So again, this is a reduction that we try to take the problem, massage it to a problem we can solve, and it turns out with some algebraic tricks you can do this. And you can do this even if the sigmas are different, as long as they're spherical. This is really the idea. And then you can just plug in the sample complexity bounds. So are we good with that? So now comes for the really hard question, which is all of the tricks we knew how to solve up to now were basically reductions to this orthogonal tensor decomposition. But the zero mean case is really screwy because our tensors don't really look like this. They're kind of getting constructed from PSD matrices with indices screwed up. Right, so this theorem is what the fourth moment of a single Gaussian looks like. So this theorem, I think it's called the isosceles theorem. It basically says that suppose X is a multivariate Gaussian, and we look at the 2mth moment of this Gaussian. And so we look at indices I1 to I2m. All the odd moments are 0. You can write the even moments of a single Gaussian as basically a sum over perfect matchings of the indices times the product over the pairs of the indices of u and v. Basically a generalization of this object. So if I go to the 6th moment, I'm going to have 3 objects like this, where I'm commuting the indices up. And this is a neat question, because somehow our tensor is being made of mixtures of PSD matrices. And now let's just say I give you this object. Can you reverse engineer these covariance matrices? And this is a problem I was bugging a lot of people about for the last few years, trying to say, how do you recover PSD matrices that are mixed up in this way? And we thought a fair bit about this, and we actually were trying to use some work by Pablo. So you had this paper with Ben Recht and Fazel on kind of trace norm minimization. So the main observation is, if you have, suppose we just look at the 4th moment. What we'd really like to do is make a tensor, let's call this x4, where the columns are these PSD matrices. Right? If I didn't have these two terms, this would be great, because I just view this tensor as a matrix, and I just want to say my columns are these matrices. This is what I would really like to do. Just say that, basically I just want to say I can make a problem where instead of mu i's, I have sigma i's here, where the sigma i's are just, the matrix as a vector. But the problem is you can't get that because they're mixed up. But the key observation is the way that they're mixed up is a linear transformation. Because what we have is this. We'd like an object where that it looks like this, where you have sigma across sigma, where you can think of each sigma as a vector. And these objects are linear related. In fact, we know the coefficients in which they're linear related because they're exactly coming from these perfect matching theorems. But it turns out the conditions one need, at least from these, it's sort of coherent in the worst possible way, that at least inverting this system is never going to work, and even going to higher orders won't work. But you keep banging on this for a while, and basically the idea is there's sort of 2 steps now to solve this problem. Well, really 3. The first step is try to figure out the range of these PSD matrices. So we have a set of matrices. Try to find the range. This is non-trivial, but if you start playing around with projections of these objects, what you start seeing is projections of higher moments of this Gaussian basically look like projections of these matrices, but you also get weird rank 1 components. But it turns out you can do this to get the range of these matrices. And then the point is if you knew the range of the matrices, you can then think about solving this problem in a different basis. And then we can argue it's invertible. Okay? So the game is kind of, at a high level, the game is still, we're going to reduce it to a problem like this, where we make tensors out of the PSD matrices. So each mu I is going to be a matrix. But we're going to do it through some algebraic manipulations. Okay. So it turns out even in this very general case, it works, and the conditions we need. So now we just need to be in a sufficiently high dimension to get enough parameters. And that's going to be the number of Gaussians need to be bigger than the dimensions squared. And we think that can be relaxed. And then we can actually show in a smooth analysis model this works, where it's really the strong version of smooth analysis. You know, with sort of exponentially small probability, there's a failure probability, and you really will solve this sort of mixture PSD matrix problem. So basically, the high-level point there is these techniques really seem to go the distance, and that's an interesting, it's sort of an interesting observation. Like, were they somehow limiting? But it does feel like for the non-degenerate cases, if we're in reasonably high dimension, these things are in fact generically solvable, and they're sort of generically solvable, you know, in a smooth analysis problem. So to just wrap up there, you know, you can look at the papers for solving LDA. It's sort of a similar set of tricks, but again, it's a much easier set of tricks to get that to work out. So in summary, basically looking at these problems as inverse moment problems is a helpful way to give us insight. And you know, the algorithms seem promising because basically these tensor methods, you're trying to find local minima of sort of skewness and fourth moment maximizer. You're basically trying to find spiky directions in your data. And as a heuristic, this seems like a good idea. But what's interesting is it also seems to go the distance in some of these harder problems with some tricks. So, you know, this has been joint work with a number of very talented people. Daniel was working with me on this stuff from the beginning, and Anima has, you know, been a part of most of this work, and she gave a very nice talk on related work a few days ago. Most recently, this very difficult problem of learning a mixture of zero mean Gaussians, which is really decomposing a tensor that's being made up of PSD matrices jumbled together. This was really solved by some wonderful colleagues. So Rong is a postdoc at MSR in New England. Yeah, he's really terrific, and I had a number of extremely talented interns this last summer, and Ching Ching was one of them at MIT, and yeah, she was stunning. I mean, this was sort of her first foray into ML, and they really made some wonderful progress on showing how you can actually recover this tensor made of PSD matrices. So, thanks.
So to recover this, the matrices, what is the degree of moments?
Right, so this is a good question. Because I'm saying, you know, these systems are solvable, and basically we use the sixth moment, and we need the number of Gaussians, k, to be bigger than d squared. I'm going to say d squared is in the smooth analysis model. We believe we can definitely do it in d to the 1.5 generically, but we just don't know how to show, meaning generically the set of problems it fails on is measure 0. But if we want it to actually you know, perturb it and really work with high probability, we need d squared. But if you keep going to higher and higher moments, I believe we can bring this down to d, which basically says, forget about sample complexity a moment and just ask the smooth analysis, and just ask how many Gaussians can we learn in d dimensions using this technique. And with higher moments, I think you can bring it all the way down to d, or constant times d.
If you go to the exponential sample complexity, then you can solve the whole problem.
This isn't sample complexity issues. This is getting a polytime algorithm, and we don't even know how to prove identifiability for the general. Actually, that's not true. We don't know how to solve the equations when k is less than d, because somehow, somehow you're mixing up PSD matrices in d dimensions, and we just don't know how to. It's like natural.
Using this technique, because using general algebraic geometry, you know that they're solvable.
Well, I mean, that takes proof, because you have to show that these equations have unique. Okay, right. So in certain cases you can show uniqueness generically. Solving them, like, yeah, there's just some horrible set of algebraic equations, and we have no idea how to solve.
Well, there are There are solvers, but you
Yeah, they're solvers, but like, you know, even saying that these, you know, that it works in poly time, who knows?
Well, not poly in the number of the degree. It's poly in the rest of the thing, but not poly in the...
It's not poly in K, and even then, like, it's murky what the algebraic solvers get you. I mean, look at this.
Reason why it becomes solvable if you have enough mixture components? It seems to get harder with more.
So think of it as, it's not, sorry, did I botch this? Sorry, I'm sorry, no, this is totally wrong. What? It's like this, other way. Yeah, sorry, this is yes, the worst case is a mixture of Gaussians on a line that are all zero mean. Yes, because this is the right way, and it's sort of a parameter counting argument. So as long as, you know, we think we can drop this down to k less than d, and, you know, like how many parameters do you have for PSD matrix? It's like, you know, n choose 2, and you're in n dimensions. But it's wacky because with this technique, going to higher moments, we don't know if you can solve things any more easily. And this is just this funny thing about these way these counting theorems work. And I was talking to Santosh about this years ago. As we go to higher moments, somehow, yeah, we couldn't. With the other cases, there's a reason to believe if you go to higher moments, you really can get k to be bigger than d.
Can you say some word more about the fact that you choose orthogonal summands? I don't understand, because most of tensor just do not have an orthogonal decomposition. So you assume the
right.
Space.
Yes. So the point here is, as long as k is less than d. Okay. So think of just randomly projecting your tensor down to a matrix. Right. Then you get a sum of mu I. Okay.
So you choose a metric.
Yeah, but the point is, you can as long as k is less than d, you can make these vectors. You can work in a basis to make them orthogonal, and this I think is a deep question, because if k is bigger than d, can you actually? No, but it's even an identifiability question. How many can we unpack from there? And there's a really beautiful result by. The algorithm is called like FOOBI, fourth order only blind deconvolution by, I don't know how to spell his name, Delatauer is one of the authors. And basically they argue with a 4 tensor, if it has d choose 2 objects in it, you can recover them all exactly. And this trick clearly won't work, but you can, yeah, so you know this trick. It's a really...
The topic has a nice solver as a toolbox of MATLAB. And works very well, but only for small rank, of course.
Right, but this one is at least an algebraic method which really shows identifiability generically when k is about d choose 2, and it shows that the fourth moment can exactly figure it out, which is impressive because you can't make this orthogonal, so the simple trick doesn't work. And it's a beautiful paper. It's like a page, line by line, everything makes sense, just the intuition is murky. But it's short. So you know, you kind of expect this at some level because you get more parameters as you go to higher moments. But this is neat.
So, no questions? Just thinking of the video again.